What is up, indeed? Well, one thing that's up is, as of right now, we are a month into our new material, or new material, into the course material, into the amount of stuff you'd normally cover during a semester. So we've covered a lot of stuff, and our first exam is already looming. We've done this in 2 weeks. This is the nature of the summer session. So yeah, and we've got to keep on rocking. If you have not had a chance to read my most recent announcement, I highly recommend that you pop over to Canvas and do so. It outlines, the information concerning the exam in detail, giving specific points breakdowns, etc. There's a couple things that I want to touch on. So, exam 1. Oh, let's not paint this thing. There we go. Exam 1 is coming up this weekend. It opens on Friday. It closes Sunday, and again, all of these are midnight. So it opens 12 a.m. Friday, closes 11:59 p.m. Sunday, and it covers chapters 2 through 4. Chapter 1 was very, very, very introductory, and when I sat down to write questions for the exam, I was like, what can I write on? And I considered doing stuff on like mixtures, pure substances, all that stuff, but I decided to axe that and just focus in on 2 through 4. Oh, Jen, you are welcome. In my word, not my words, in Jen's words. If you haven't taken a look at the post on Canvas, in Jen's words, I went into ridiculously extensive detail. So thank you. Hopefully it will help you allocate the amount of time you spend studying on each topic. You can also see if you're shaky on a topic, you're like, oh, well, hey, that's actually 7.5% of the exam, for example, is unit conversion. So you know to spend about 7.5% of your study time, maybe more if that's what you struggle with. Another thing to be aware of is I use problem banks. When I say use problem banks, this makes it sound like they exist out there. I write problem banks. So, like, for one exam, I end up writing, like, I don't even know how many exams. I haven't calculated that yet. But each exam has a certain number of problems. So, for example, 7.5% are unit conversion problems. But what I do for the handful of unit conversion problems you write, they'll be selected at random from a much larger bank of problems that I've created. And so each exam, though it tests on the same things in the same proportions at the same difficulty level, will have a unique set of problems. And as I pointed out, because it's randomly generated, there is a chance of 2 students pulling the exact same exam, but that chance is 0.0000. Is it 4 zeros? Yeah. 0.0006% chance of 2 exams being identical. So your chances are very, very low of having the same exam as someone else. So Again, it's open book, open internet, open other humans, but if you're going to collaborate, be smart about it. Don't say, hey, what'd you get for number 2? Because if they say A and you click A, yours is going to be different than theirs. Okay, let's see, Jen. Not just to know what to study, but less stress on what's there. Oh, thank you. Yes, totally. I'm a huge believer in giving you information to focus your study time effectively. I don't want you wasting time like memorizing stuff that I don't think is important and won't be testing you on. So that's kind of the motivation behind the post. And again, if you haven't seen it already, you can check it out. In other news, and I'm going to be posting this as an announcement to Canvas later, but I just wanted to let everyone know. So lab exercises 1+2, which was 1 unit, and 3, as well as lab quiz 1+2 and quiz 3. These have all been graded. All right, I still haven't made it to the prereq exam. That's next in the queue, but I graded the lab exercises, entered those grades, and I graded the free response questions from the lab quizzes. Those are entered as well. So as of right now in Canvas, many people threw at me the question like, is the grade that it says for my quiz my actual grade? And I kept saying no, it's just your grade on all the rest of it, but I have to grade the free response questions. Now those are graded. So now in Canvas, your current grade will reflect everything up until the third lab. Lab 3 and quiz 3 are all current. I saw there's some eager beavers who've already submitted stuff for lab 4. I haven't touched those. I'm going to wait till everybody gets those in, but all the lab stuff up to 3 is current in the grade book, so you can see your grade reflected there. All right. Well, I am a little bit surprised. As of right now, we're actually on pace lecture-wise. I haven't fallen behind yet, which normally I do. So, yes, the prereq exam is the one thing that I haven't got to yet. Oops. There we go. Yeah, the prereq exam is next on my list. So anyways, actually the reason why I tackled the lab stuff is because I thought those will take longer to grade. Correcting the prereq exam will be shorter. So I tend to, when I'm grading, tackle the biggest challenge first and then work my way to the rest of it. Yeah, no worries. I think the extra credit closes today. So right. So extra credit 1 closes tonight. After it does, yeah, so I can't do any adjusting to it while the assignment's open. After it is, then I'll take a look at it. Okay. All right, I think that is all the business stuff that I have. As I said before, we're actually on track with the tentative lecture schedule. So let's go ahead and dive in. So chapter 5. Chapter 5 is the foil, is the counterpoint to chapter 4. Yeah, totally. So So with chapter 4, we were looking at ionic compounds, ionic bonding, structures, Lewis structures for ionic molecules, and we looked at what was holding those ionic compounds together, and the answer is the ionic bond, right? The attraction between the positive cation and the negative anion, that creates the ionic bond that holds those molecules together. Now, all ionic bonds are created when electrons are taken, right? The more electronegative nonmetal steals an electron from the less electronegative metal, and that's what creates the charge separation. And I want you all to know that stealing electrons from metals is not the only way to form a bond, all right? There's a better way, there's a more peaceful way, and it is called the covalent way, all right? So we are going to look, in chapter 5, we're going to explore something known as a class of molecules known as covalent molecules, and they're called this because they form covalent bonds. All right. Now, or I don't know why I put this in the plural. So a covalent bond is a bond where two or more, doesn't have to be just two, but it has to be at least two or more electrons are shared between two nuclei. All right? It's a bond where two or more electrons are shared between two nuclei. Okay, now how does this, what exactly are we talking about? How exactly does this happen? All right? I want you to take, as our first example, let's look at a molecule of hydrogen. All right? Now, in an ionic bond, right, we're going to look at hydrogen, and let's just compare it to something like lithium chloride. All right? Now, in lithium chloride, you have lithium, who wants to lose one electron, right, to be like helium, and you have chloride, who wants to gain an electron to become like argon. And what happens is lithium gives its electron to chlorine, becoming a cation. Chlorine steals that electron away from lithium to form an anion. Lithium is now positively charged, chlorine is now negatively charged, and that is the ionic compound. And they're both satisfying the octet rule. They're both gaining that stable noble gas configuration, lithium by losing, chlorine by gaining. Now, when you compare H2 and you look at the two atoms involved, one is hydrogen, the other is hydrogen. Now, the thing here is they both of these hydrogen atoms both want to gain one electron. All right? They both want to gain one electron. With lithium and chloride, you had this very pleasant situation where lithium wanted to lose one, chlorine wanted to gain one, and so it worked out. But here, both of these hydrogens want to gain an electron. And if one hydrogen were to steal an electron from the other, then yes, the octet rule would be satisfied for the thieving hydrogen, but the other one would be left without any electrons, one electron further away, right? So we have a situation here where they both want to gain an electron, the octet rule for both of these molecules cannot be satisfied by one atom stealing an electron from the other. Instead, what they do, rather than stealing an electron, is they move closer to each other. The two hydrogens move together, all right? And what happens is the two nuclei smush their electrons together. They kind of form an electron sandwich, and they share their electrons between the two nuclei, all right? These electrons here, which I'm circling, are shared between both atoms. All right, and that's of critical importance. They're shared between both atoms. That means that each hydrogen has access to 2 electrons. So the octet rule here is satisfied. All right? It's satisfied because in sharing their electrons and pooling the resources, each hydrogen has access to 2 electrons. That's what it wants. That's what it needs to satisfy the octet rule. All right? And so this, I'm just going to redraw. My molecule right here. These 2 shared electrons, this is called a covalent bond. And what holds these 2 atoms together in a molecule is if they were to separate, they both lose their noble gas electron configuration. They both lose the stability that comes with that. And so they will stay together to maintain that bond, to preserve their access to 2 electrons. I should say that this is a covalent bond, right? 2 electrons being shared between the nucleus. Now, you can draw them, a covalent bond, as 2 dots kind of sandwiched between the nucleus, and your book does this a lot. But I'm not a fan of that nomenclature. It gets particularly cumbersome as you move to larger molecules, and it's just, in general, it's not used that frequently. The way a covalent bond is normally depicted is as follows. Rather than show 2 dots between the nucleus, just a line. All right. So this is also a covalent bond. All right, and it represents 2 electrons being shared. All right. So if someone, okay, so that is how we draw the molecule. If someone were to ask you to draw the Lewis structure for H2, right, for hydrogen, the answer would be like this. You draw the 2 H's with a bond, a single bond in between them, and that single bond represents the 2 electrons being shared. All right? So this is a covalent bond. Rather than stealing and giving electrons, right, there's no electron muggings here. We're just peaceably sharing our pooled resources to attain the stability that we need. All right? So that is the Lewis structure for H2. All right, let's do another example. Let's look at the Lewis structure for water. All right. So let's look at the Lewis structure for water. Now, we already know that hydrogen has a Lewis structure of a single dot, right? This is hydrogen. Oxygen has 6 valence electrons, so its Lewis dot structure will look like this. All right. Now we'll form our first bond by overlapping, by sharing that unpaired electron on hydrogen with the unpaired electron on oxygen. All right. That'll create a covalent bond, right? If we share hydrogen's one unpaired electron with one of the unpaired electrons on oxygen. But you'll notice hydrogen has 2 electrons, octet rule satisfied. Oxygen only has access to 7 at this moment in time. But that's the reason why we have 2 hydrogens, right? We bring in a second atom of hydrogen, we form a second covalent bond, and this is the Lewis dot structure for a molecule of water. Now, just to round things out, let's add in, let's draw our covalent bonds like lines, like civilized people. All right, and this right here is the Lewis structure for water. All right, water has 2 single bonds, and in addition, we have 2 what we call electron lone pairs. All right, these lone pairs are right here. All right, these are called electron lone pairs. They're also called, they're electron lone pairs, or sometimes they're called non-bonding electrons. I'm actually going to clean this up a little bit. All right, those are our electron lone pairs or non-bonding electrons. There's 2 electrons in each lone pair of electrons, right? Because that's why the word pair is involved. So this would be the Lewis structure for water, again, built from the Lewis dot structures of each element involved. All right. Now, the book kind of favors this method rather heavily. The one where you draw the dot structure for the atom and then use those, kind of smush them together to build your molecule. Now, the book favors it. It does have its merits, but I find in general, for the structures that we run into in this class and in general chemistry, that this method has some drawbacks that are pretty significant. So I am going to teach you a method for drawing Lewis structures. I'm going to teach you a modification of the method that I teach to my Chem 400 classes. And if you're wondering why the modification, well, some of the molecules that we deal with in Gen Chem are a little more complicated than the ones that we deal with here. So we can kind of use a simpler scheme to draw Lewis structures. The only reason why I'm mentioning it is if you plan on attending the after party for Chem 305, which will be Chem 400 this fall, which I'm teaching. If you attend that after party and we get to the part with Lewis structures, and I start teaching you how to do it, and you're like, hey, you didn't teach us this. It's because we don't need quite the full metal version here in this class to draw the Lewis structures that the book wants us to draw. So again, it's going to be slightly simplified next semester if you're taking Chem 400. It's not that I was lying to you, it's just we didn't quite cover it all because the book doesn't cover the same complexity of molecules that the Chem 400 textbook does. So with that in mind, I'm going to teach you this way of drawing Lewis structures. And I should just say up front, if you like doing the dot structures, like drawing the dot structures for the atoms and kind of like connecting them like Lego pieces, you can totally do that. It's totally fine. But the method that I'm about to show you, I think is a better one, but if you're more comfortable with this one, they both get you to the correct answer either way. All right. So with that, let's talk about drawing Lewis structures. Here's the step-by-step breakdown. For drawing Lewis structures. All right, step number 1 is total your electrons. I should say the valence electrons. Step 2 is select the central atom. Step number 3 is attach the other atoms. Step 4 is complete your octets. And step 5 is add charges. All right, so this is our step-by-step method for drawing Lewis structures. Let's see. Actually, I kind of like it over here better. Let's go ahead and leave it there. There's our step-by-step method. Let's apply this. All right. So what are we actually talking about? Let's take a look at our first example. Let's draw the Lewis structure for CH4. All right. So here's kind of the method, the mindset that you want to take going into this. Is we have a certain number of atoms in our molecule, and we need to figure out how they're connected. All right. We need to bond them to each other, and to make bonds and to satisfy octet rules, it takes electrons. So we need to know how many electrons are in our budget. All right. Now, when you count these up, you must spend your exact electron budget. Exactly how many valence electrons, that's what you must use to build your molecule. You can't go over budget, you can't go under budget. All right? So here, let's total our electrons. Carbon, when you look at the periodic table, has 4 valence electrons. Now, hydrogen just has 1, but we have 4 hydrogens in our molecule, so that gives us a total electron budget of 8 electrons. All right, that's step number 1, down. Step number 2, select the central atom. All right, now your central atom is going to be a general rule of thumb is It's going to be the element that you have the least of. All right? That's going to be the atom that you put in the middle, and here, for CH4, that element is carbon. All right? So we're going to use carbon as our central atom. Step number 2 is done. Step 3, attach other atoms. So we have here 4 hydrogens that we have to attach. And in order to attach these atoms, so let's just start by attaching 1 hydrogen to our carbon. To do that, we got to make a bond, right? And 1 covalent bond costs 2 electrons to form. So when you draw that first bond, you need to subtract 2 electrons from your electron budget, leaving you with 6. Let's attach another hydrogen. Well, to do that, to make that bond, we need to spend another 2 electrons, leaving us with 4 in the budget. To attach our third hydrogen, we'll take 2 more electrons, leaving us with 2. And then our fourth and final hydrogen, to make a single bond to that hydrogen, requires 2 more electrons, leaving us with 0. All right, that is our whole budget so far. Step number 3 is done. Step number 4, complete our octets. All right, carbon wants 8 valence electrons, just like neon. Hydrogen wants 2, just like helium, right? And if you look at each hydrogen in this molecule, each hydrogen has 1 bond, which holds 2 electrons, so every hydrogen has its octet rule satisfied, right? 1 bond equals 2 electrons. And if you look at carbon, carbon has 4 bonds, which means it has 8 electrons. So both carbon and hydrogen have a satisfied octet in this example. All right, and when it comes to add charges, we get to ignore this for now because we did not have an ion to begin with. So CH4 is not an ion, so we don't need to worry about charges here. All right, so that is the Lewis structure for CH4. We used all of our electrons to make it. We used all of our atoms, and octet rules were satisfied for each atom in the structure. Cool? All right, it's been super quiet on the comment front. Do you guys have any questions? Any questions so far? I've got several more examples queued up, but if there are any questions or if you have any doubts about how things are working, let me know. Okay. In the absence of any questions, let's do our next example. Let's draw the Lewis structure for F2. All right. Step number 1, we need to know how many valence electrons we're dealing with. Fluorine, okay, good. I'm glad to hear it. Fluorine has 7 electrons, but we have 2 of them, right? We've got 2 fluorines in this molecule. All right, awesome. That's excellent news. I get nervous when nobody's asking questions because it either means everyone gets it or no one gets it. But I'm glad that it's actually because it's making sense, or seems to be. If it's not making sense, don't let that make you more shy. Totally shoot out your questions because we have the answers. All right, we have 2 fluorines in this molecule. each with 7 electrons. So we have a total of 14 electrons to spend. All right, that is step number 1. We total our electrons. Selecting a central atom here is kind of pointless because we only have 2 atoms. So there isn't really going to be one central to the structure, but that's fine. All right, now we need to attach them. And to attach it is going to cost 2 electrons out of the budget. Yes, Esther, we totally will. We're just building up to it. Corinne's a great question. Only valence electrons are used in bonding. Yep. So you don't look at the total electrons, you look at the column it lies in on the periodic table. All right. Excellent. So we spent 2 electrons out of our budget to bond them together. Right. We're already done with steps 1, 2, and 3. Step 4, complete octets. Now, if you look at this fluorine, right now, this fluorine has 1 bond. In that bond, there are 2 electrons, right? So as of right now, we have 2 electrons, but we need 8, right? We need 8 electrons to have our octet rule satisfied. So we've already bonded, we've already made all our bonds. Yes, the column trick is clutch, Jen. Totally clutch, and you're welcome. We need to use the remainder of our electrons to complete octets. And you'll notice this fluorine has 2 electrons. It needs 6 more. So we can spend 6 electrons out of our budget to complete this fluorine's octet. And the way that you show that is by adding 1, 2, 3, 4, 5, 6 electrons to that fluorine atom as non-bonding electrons, all right? So now this fluorine has 1 bond, which is 2 electrons, but it has 3 lone pairs, which are 6, giving this fluorine a total of 8 electrons, full octet. All right, let's look at the other fluorine atom. All right, this fluorine right now has 1 bond, which is worth 2 electrons. So it needs 6 more, and you'll notice that we have 6 more electrons in our budget. We have enough electrons to add 3 lone pairs, 1, 2, 3 lone pairs to this fluorine to give it 6 more and complete its octet. So that's what step 4 is talking about when it says complete the octets. After you've attached all your atoms together, you need to look at each individual atom in your structure and make sure that they all have the electrons they need, right? And that'll be 2 for hydrogen, 8 for pretty much everything else, right? Because that's why they call it the octet rule. And again, we do not need to worry about adding charges yet because we did not begin with an ion. Here, sorry, hang on. Just got a thing that I gotta... Okay. Okay. So that is the Lewis structure for fluorine. Okay, sweet. Awesome. Awesome. It's the rare moment where chemistry makes sense. What kind of Mad Monday are we dealing with here? Let's do another example. Let's look at O2. All right, now here, oxygen, 6 valence electrons, but we have 2 of them, so we're going to have a total of 12 electrons to spend. All right. Again, the central atom in this instance doesn't really make that much sense because we only have 2 to speak of. Attaching these together, let me write this in black. Making that single bond between the 2 oxygens is going to cost us 2 electrons. All right, now let's take a look. At this oxygen right now, there's 1 bond, which means it has access to 2 electrons. We need to give it 8 total, right? So we can spend 6 out of our budget to complete this oxygen's octet. There's 1 bond, 3 lone pairs, add 6 more electrons to the mix, giving us a total of 8 electrons. All right, now let's look at this second oxygen. We've got 1 bond, which has 2 electrons. You'll notice that we need 6 more, but we only have 4. So you can't just automatically give every atom all the dots that it needs. You're limited by the number of electrons you have. After we give oxygen 1, 2, 3, 4, now as drawn in this structure, it has 2 lone pairs, 1 bond. So that's 4 electrons plus 2 electrons is 6. And we've got a problem. When you're drawing Lewis structures, you must complete the octet rule. If you don't, it's incorrect. All right? So we need to make sure every atom has 8 electrons, but we're out of electrons to give. You might feel like you're in a bit of a catch-22. All right, now, this is a situation that is super common, all right? Super common when you are, whoops. There we go. This is a very, very common situation when you're drawing Lewis structures, and it's going to feel like you are, quote unquote, missing 2 electrons. All right, we're not. We calculated our electrons correct, but if we only had 2 more, this would be easy, but we're down 2. How do we complete this octet? Whenever you're missing 2 electrons, quote unquote missing 2 electrons, the way you solve this is the same. What you're going to do is take one of the lone pairs away from this oxygen, and we're going to turn it into a second bond. All right? Let me show you how this turns out. All right? I'm just going to redraw my structure the way we had it. We had a bond there, except where initially I had 3 lone pairs around that green oxygen, I've removed one of those lone pairs and I've turned it into a second bond between the two oxygen. Yes, we're going to share. Sharing is the solution. Sharing is the solution. When you look at the two oxygens in this structure, all right, this greenish one has 2 bonds, well, giving it access to 4 electrons, and not 3 lone pairs, 2 lone pairs, which have another 4. So together that's 8. Octet rule satisfied. When you look at this one, the one we're using blue for, we have 2 bonds, 4 electrons, 2 lone pairs, also holding 4, giving our second oxygen access to 8. All right. Octet rules are satisfied. We used the correct amount of electrons that we had to spend in the structure. This is our Lewis structure. All right, again, we're not dealing with an ion yet, so we don't need to worry about adding charges. Now, this situation you're going to run into over and over. Whenever you're drawing a Lewis structure and you find that you are quote-unquote missing 2 electrons. Like if you just had 2 more electrons, you'd have it made, but you don't. The solution to this, when you're 2 electrons short, is you want to make, or I should say use, a lone pair to make a double bond. All right, use a lone pair to make a double bond, and that is exactly what we did between these 2 oxygens. All right? Yep, totally, because it takes exactly, Jen, it takes 2 electrons to make a bond. So if you've got a single and you have a lone pair, you can take that lone pair and use them to make a second bond out of those 2 electrons. Let's do another example. Let's do nitrogen, N2. Nitrogen has 5 valence electrons, and if we have 2 of them, that means our initial budget will hold 10. Again, we don't really worry about a central atom here. We've attached them all. Now let's fill out our octets. If we give 3 lone pairs to this nitrogen, that's going to spend 6 electrons. Oh, hang on. Whoa, math. Before I do that, first, it takes 2 electrons to make that bond, right? So now we're left with 8. Adding the blue lone pairs, we'll spend 6 electrons out of our budget, leaving us with 2. So the nitrogen on the other end, we can only give 1 lone pair to because we only have 2 electrons left in the budget. We've completed the octet for one nitrogen, but not for the other, right? The blue one is fine, but the green one right now has one bond, which is 2 electrons, and 1 lone pair, which is another 2, right? It's got 4, it needs 8. Well, we know what happens what we need to do when we're missing electrons, right? Let's remove a lone pair, turn it into a double bond. All right, now we don't have 1 bond on this green nitrogen, we've got 2, which means that we have 4 electrons plus our lone pair. Still not enough, right? Still not 8. We're still missing 2 electrons. Well, if we've done it once, we can do it again. Let's take a second lone pair from that first nitrogen, turn it into another bond, see what happens. Now we have 3 bonds, 6 electrons, plus the 1 in the lone pair, means we have 8 full octet. If we look at the nitrogen that we were quote-unquote taking electrons from, taking lone pairs from, right now it has 3 bonds, 6 electrons, and 1 lone pair. It has a full octet as well. So in this one, we weren't missing 2 electrons, we were missing 4, but the trick that we could use to make a double bond can also be used to make a triple bond. When you find you're missing, quote unquote, well, I should say, this is a triple bond. All right. Is there a limit to how many bonds you can have between 2 atoms? Jen, that is a great question. So, yes. In this class and the next, that's like in this life and the next, you will never see more than a triple bond. There are some elements that can have a higher bond order than a triple bond, but they're transition elements, transition metals. There's some that can do that. You don't have to worry about that here. We're only going to be looking at main group non-metals when we talk about drawing Lewis structures. So higher bond orders exist, but we won't be studying them in this course. All right. Let me pause for just a second to look where we gotta go. Okay, let's do a few more examples. So first, let's draw the Lewis structure for formaldehyde. All right. Step number 1: total valence electrons. Carbon has 4, oxygen has 6, and hydrogen has 1, but we're dealing with 2 hydrogens in our molecule. So we'll have a total of 12 electrons to start. All right, now when it comes to selecting the central atom, I said just go with whichever atom has the fewest, right? But here, is it carbon or is it oxygen? Because we have 1 carbon, we have 1 oxygen. Which one goes in the center? And the answer is, when you're kind of in a predicament like this, when you're in a tie, you want to select a central atom that makes the fewest number of bonds. All right, and here's how you can spot that. If you look at the Lewis dot structure for carbon, it's got 4 unpaired electrons, whereas oxygen has 2 unpaired electrons. The number of unpaired electrons tells you how many bonds an element likes to make. So carbon likes 4 bonds. Oxygen, because it has 2 unpaired electrons, likes 2 bonds. Under normal circumstances, it can make more, but in general, it likes 2. Carbon likes 4, so we're going to select the element that likes to make the most bonds as our central. All right, we're going to put carbon in the middle. Step 3, we need to attach all of our atoms to our central atom. And here, you'll notice we have 3 atoms to attach. This will take 2, 4, 6 electrons to make all of those covalent bonds. So we have 6 electrons left. So we've attached our atoms. Now it's time to complete our octets. All right, oxygen right now has 2 electrons in its bond, right? We know it needs 8. So it needs 6 more electrons. 1, 2, 3, 4, 5, and 6. And you'll notice that spends the remainder of our budget. We have no more electrons left over. We have no more electrons left over, but carbon right now has 3 bonds, which means it only has access to 6 electrons. It needs a total of 8, and whenever we're missing 2, that's when we take one of our lone pairs and turn it into a multiple bond. Now carbon doesn't have 3 bonds, it has 4, which means it has access to 8 electrons. If you calculate oxygen, it has 2 bonds, which is 4 electrons total in those 2 bonds, and 2 lone pairs. So 4 plus 4 is 8. Each hydrogen has 1 bond, so it has 2. This is then the Lewis structure for formaldehyde. All right? Okay. Now, let's look at... so we've, up to this moment in time, we have been only looking at elements that don't have charges. Let's take a look at a few ions, all right? For example, let's draw the Lewis structure for formaldehyde. You may be wondering, wait a minute, what am I talking about? Drawing covalent Lewis structures for ions. You're like, I thought ions and covalent compounds were 2 different things. Well, you remember your polyatomic ions, right? Those are all, every polyatomic ion is a covalent compound with an overall ionic charge, okay? And the only difference for drawing a Lewis structure of a polyatomic ion is how you total your electrons overall. So in that first step, we know that oxygen has 6 valence electrons. Hydrogen has 1 valence electron. All right. Now here's where you take a look at the charge. A charge of -1 means that there's 1 extra electron. That this compound has 1 more electron than it should have. As a result, that charge of -1 means you need to include 1 more electron in your total electron count. All right, so that means that we have 8 electrons to spend. Well, here we don't really have to worry about a central atom because we have an oxygen and a hydrogen. We attach them together at the cost of 2 electrons, leaving us with 6. Now we need to complete our octet. And hydrogen satisfied, oxygen needs 6 more electrons. We've got 6 in the budget. So we add our 6 electrons in the form of 3 lone pairs. And finally, last step, we need to add our charges. Now, this molecule has a charge of -1. So the way you depict that is you put the entire Lewis structure in a bracket with the charge of the ion on the outside of the bracket. All right, that is how you denote that this is a charged species, and that is the Lewis structure for hydroxide. All right. Let's take a look. So that's how you handle ions with negative charges. Let's look at an ion with a positive charge. Let's look at hydronium, H3O plus. All right. Now again, just like with our anionic example, the only difference is going to be we have to add the charge at the end, and it affects how you total your electrons. So oxygen has 6, hydrogen has 1. Yes, Jen. Hydrogen wants the same number of electrons as helium, and helium only has 2 electrons. That means hydrogen's oxide rule So hydrogen wants the same number of electrons that helium has, right? That's its nearest noble gas. Helium has 2 electrons, so hydrogen's octet rule is satisfied with one single bond. You'll never give lone pairs to hydrogen. It just wants to make one single bond and then it's done. Then it's satisfied. All right, now totaling our electrons for hydronium. We've got 3 hydrogens, each one brings 1 electron. But now we have to talk about how to handle our positive charge. If you have a charge of positive 1, that means that this compound is missing 1 electron. All right, it has 1 electron less than it should have. So when you have a positive charge, you have to subtract 1 electron from your total your total electron count. So 6 plus 3 is 9, minus 1 is 8. We have 8 electrons to spend. We've totaled our valence electrons, our central atom. Yes, totally. Totally, yeah. It's you just look to the nearest noble gas. It's just a matter, Jen, you got it exactly correct. It's just a matter of getting the reps in. All right, so our central atom is oxygen. We need to attach all of our hydrogens to this oxygen. Doing so, because we have 3 of them, 2 electrons per bond, it's going to cost us 6 electrons in total. Oh, look at all these steps. We've selected the central. We've attached the others. Now we have to complete octets. Each hydrogen is satisfied with 1 bond because it has 2 electrons. Oxygen right now has 3 bonds, which means that we have 6 electrons. We need 2 more, and look at our budget. We have 2 more. So we give it 1 lone pair. And now oxygen's octet rule is satisfied. We've completed our octets, and now for our final step, we need to add our charges. We throw a bracket around hydronium and add our charge of +1. Cool? All right. Let's do 2 more examples, and then we will call it a day. So first, for our second to last example, our penultimate example, let's do carbonate. All right, we've done +1, -1. What about -2? All right, here, carbon has 4 valence electrons. Oxygen has 6, but we're dealing with 3. Right, so 3 times 6 is 18. And now, we've got a -2 charge. That means that there are 2 extra electrons in this structure. So we're going to have 18 plus 2 is 20, plus 4 is 24. This is the biggest budget Lewis structure we have ever dealt with. And we've just finished totaling our electrons. Carbon is going to be our central atom. Next step, we need to attach all of our oxygens. Doing so will cost us 2, 4, 6. 24 minus 6 is 18. Now, our first oxygen has 2 bonds. It needs, 2 electrons. 1 bond, 2 electrons. It needs 8 electrons. So if we give it 3 lone pairs, it's got a full octet. We got to take 6 out of our budget. Our next oxygen, 1 bond, needs 3 lone pairs for a full octet. So let's do it. Give it 3 lone pairs. Take 6 out of the budget, which leaves us with 6. That's kind of perfect, right? Because our last oxygen needs 6 electrons. And we have 6 electrons to give. Now we're out. All of our oxygens are satisfied. But notice that carbon is not. This carbon has 3 bonds, and that's it. This carbon only has access to 6 electrons. We're in that same old situation where we're missing 2. So we're going to take one of our lone pairs, and it doesn't matter which oxygen you pull from. Just one of your oxygens. Take its lone pair, turn it into a double bond. So now carbon has 8 electrons as well. Each oxygen, as we know, is already satisfied. The octet rule. So the final step is to bracket this guy, put the charge on the outside, and that is the Lewis structure. All right. Now, I know it's 2:29. We've got 1 minute left. There's just one last thing I want to tell you, and that is I need to tell you about a couple exceptions, a couple compounds that break the octet rule. All right, now you may hear this and groan to yourself like, no, we have to memorize exceptions, and you don't. All right, I'm not going to test you on these. However, I believe they do show up in one of your lab exercises. They may show up on a lab quiz as well, because I don't write the lab quiz for this one, so maybe on there as well. So just to be aware, there are a couple compounds that break the octet rule. The first is nitrous oxide. This Lewis structure looks like this, and no matter how you do it, you won't be able to get away from this nitrogen only having 7 electrons. And you may be going, how is that possible? How can you break the octet rule? Well, nitrous oxide, turns out this thing is crazy unstable. Alright, very unstable. It'll react with almost anything to get one more electron to satisfy nitrogen's octet rule. Alright, so that's one out there. If you're drawing this Lewis structure and you can't find a way to fiddle with the electrons to make everybody happy, you never will be able to. That is the final structure. The third one is boron. All right. With BH3, the Lewis structure here will look like this. And there's nothing you can do here. Boron has 6 electrons, and that's it. Boron's a weird one. It technically is fine. It's not like happy to have 6, but it's okay with it. It can live with it. So often you'll see boron with 6 valence electrons, and it's just this really weird dude who can roll with it. Again, I'm not going to test you on these, but you might run into them in the lab exercise or in a lab quiz that I haven't written. So just to be aware, I wanted to put it on your radar, but these Lewis structures will not show up on an exam, so you don't have to be afraid of them. Cool? All right. So that is where we're going to stop for chapter 5. 5? Yes, chapter 5. As of right now, oops, no, don't do that. Let's go right here. You know how to draw the Lewis structures for covalent compounds. So if you're wondering how far into chapter 5 should you practice, you can do all the Lewis structure drawings for covalent compounds. Tomorrow, we'll come back and talk about something called valence shell electron pair repulsion theory. Better known as molecular geometries. Alright, so that will be the subject material we hit tomorrow, but as of right now, you can practice drawing your Lewis structures for covalent compounds. I hope you guys have a great Monday. Happy week 3. And I will see you all tomorrow. Later.